Welcome back, everyone. To begin the afternoon session, we are honored to introduce Professor Atul Sharma, the Rahul Bajaj Chair Professor and the head of the Department of Mechanical Engineering at IIT Bombay. The PhD from IIT Kanpur. Professor Sharma specializes in computational fluid dynamics, multi-fluid dynamics, and fluid structure interaction. His pioneering work in developing computational tools has led to impactful research and numerous publications. A fellow of the Indian National Academy of Engineering (INAE), he received accolades such as IIT Bombay's Presentation Award in the year of 2020 and the Excellence in Teaching Award in the year of 2019. Professor Sharma will share his expertise on an improved pressure integration force case level set method for 2D and 3D multiphase flow simulations. I welcome Professor Atul Sharma to begin.
First of all, I would like to thank Arvind for giving me the opportunity to share our work with you. I'm basically a computational person, so in our lab, the training is on development or improvement of existing computational methodology. Then using the developed in-house code on certain interesting engineering applications, and the data that we get from those simulations, we use those data to come up with a scientifically exciting and engineering relevant story of the problem. So we work on computational fluid dynamics development application analysis, and this is the title of the textbook also which I had written. Basically in our lab, when I joined IIT Bombay 20 years ago, we started working on developing computational methods for multiphase flow, and we used level set method. And there are a series of PhD work which has been done. So this work, there is a journey with which we had gone through level set method. When we started 20 years ago, we started with what is called as diffuse interface level set method. Then we felt that the modeling approach can be further improved, and then we came up with what we call as sharp interface level set method. It was proposed in the literature, we did certain improvements. And after working with sharp interface level set method, we realized that when you want to develop a computer program with sharp interface method, the implementation details are too messy, especially when you consider heat transfer as well as mass transfer problems. So then I got an idea that can we improve diffuse interface level set method and demonstrate that you can get a result which is as accurate as well as takes less computational time as compared to the existing diffuse interface level set method. So this talk is on an improved diffused interface level set method, where the core idea is whether we can, like in CFD, one of the common word which is used is pressure velocity decoupling. So in this talk, okay, now as far as surface tension, force due to surface tension is concerned, it's a surface force, while commonly in computational methods it is modeled as volumetric force. When we use sharp interface method, a diffuse interface method is a one fluid formulation which uses single Navier-Stokes equations, and whereas sharp interface method is a two fluid formulation which uses interfacial boundary condition as a jump in pressure or temperature for heat transfer problems. So diffuse interface method, existing diffuse interface method uses force due to surface tension as a volumetric force. Sharp interface level set method uses it as a surface force. And realistically, it's a surface force. So in a diffuse interface method, in fact, 15 years ago, when we were working on level set method, we came up with certain physical interpretations of the functions used in a level set method. This level set method was proposed by a mathematician, so there are certain mathematical functions. So 15 years ago, we had used certain physical interpretations which I'll present. And using those physical interpretation, we came up with this improved diffused interface level set method, where we have indeed implemented numerically a diffused interface level set method with force due to surface tension as a interfacial force. And then we ultimately, whenever you want to demonstrate that you have developed a computational method, the basic idea is to sell a product in a market. You want to say that to achieve the same quality, the price is low. So in the computational work, the quality comes with the accuracy, and the price comes with the computational time. Okay, so in all this series of work, what we ultimately do is we finally show some results highlighting that our improved method gives the same accuracy with a substantial reduction in computational time. In level set method, one of the biggest disadvantage is mass loss. So when you talk of accuracy, people question you whether you have plotted mass loss. So indeed, I will demonstrate, especially with this improved diffused interface level set method, the mass loss is very low. And our fundamental basis is we have tried to come up with a better pressure interfacial force coupling. So this is the computational fluid lab in which the students works on. My research interest is mainly on theoretical and computational continuum mechanics, involving both developing in-house code and methodology for fluid mechanics as well as solid mechanics. So we work on multiphysics problem, on computational methodology development as well as application for computational fluid structure interaction, where in the last, I would say, 10 years, we have worked on fish-inspired hydrodynamic studies and flow-induced structural vibrations. And last 15 years, we have been working on computational multi-fluid dynamics, where using level set method, we had done some detailed simulations for droplet collision, combustion, and nucleate boiling. Presently, we are doing simulations with our in-house codes for transient nucleate boiling. Last 5 years, we have also started working on biofluid mechanics, where along with the flow solvers, we have developed structural solver using finite volume method and also acoustic solver for sound-based detection of blockages in the artery and also for aneurysm. So we worked towards development of unified computational methodology for multiphysics problem in general. So the contributions from the development of range of novel and efficient computational methodologies and tools, its application to large number of simulation and analysis of the resulting data. We have demonstrated scientific understanding for fish-like kinematics and swimming, energy harvesting for flow-induced structural vibration, and we have also worked on sustaining nucleate boiling under zero gravity. We have a patent on one of the designs which we have proposed in this study. Technologically, I had worked with certain industry and demonstrated the applications of CFD for arc formation inside circuit breaker, radiator fan assembly of power transformer, and printed circuit heat exchangers. Academically, I proposed a textbook to make the subject of CFD easy enough to be taught as early as second year, third year of undergraduate curriculum, where I tried to bring more of physics, less of maths in the subject of CFD. Now, this talk is on level set method, which is one of the method in computational multi-fluid dynamics or computational fluid dynamics for multi-phase flow. And one of the big challenge as compared to single phase flow, when you go for multi-phase flow simulation, there are two broad main challenges. One is sudden variation of thermal physical property across the interface, and modeling of localized force such as surface tension at the interface. Now, one of the earliest and easier way of handling this modeling challenges is a one fluid approach, which considered whole domain for conservation laws. It uses a single set of conservation equation, and this is what is done in a diffuse interface method, where the sharp change, whenever you develop a computational method, any sharp change you have a numerical stability issues. So in this case, there is small thickness which is considered across the interface, across which there is a smoothing of spatial variation of thermophysical properties and interfacial forces. There is as all of us know, that surface tension, force due to surface tension is a surface force. So there is another more realistic modeling of interfacial phenomena, which is the approach is called a sharp interface approach, which uses a multi-fluid approach and consider a subdomain conservation loss as well as interfacial jump condition based formulation. Although in multi-phase flow there are a lot of computational methods, but these are one set of numerical methods for separated flows, starting from volume of fluid to front technique method to the level set method. So, as compared to CFD for a single phase flow, for like when you solve single phase flow, fluid flow, no heat transfer, then you have a continuity equation, momentum equation, and you obtain solution for spatial variation of the flow properties. But when you want to capture interface, basically there is an advection equation which is shown here. So the additional equation in multi-flow is the interfacial advection equation. Now, out of these three methods, level set method is an Eulerian method for capturing moving interfaces. It uses three functions. Level set function for interface representation. I'll show you in the next slide how do we represent interface. Heaviside function for thermophysical property calculation, and Dirac delta function for surface tension and interfacial mass transfer. So this black region is a fluid 2 and the white region is fluid 1. Then the way we define level set function, the first function is its value is 0 at the interface and there is a change in sign across the interface. So such as in fluid 2 it is negative and in fluid 1 it is positive. Now in a diffuse interface level set method, you can see that there is a thickness of the interface. This black is the physically realistic interface, phi is equals to 0, and the red band is showing the thickness of the interface. Typically, in a numerical approach, this is taken as in a Cartesian coordinate system 3 delta x. So you can see here also that the value of level set function is negative inside and positive outside. It's a normal distance function. It's a sine normal distance function. So thermophysical property are smeared across that red band using a second function which is called as Heaviside function. And this function is a combination of a linear function and a sinusoidal function. And this this results in smooth variation of interface across the red band. In one of our earliest paper in this area, we have physically interpreted the Heaviside function. If you take its value at the centroid of the surface of the control volume, then it represents interfacial area fraction. And if you take the value of the Heaviside function at the centroid of the control volume, it represents the volume fraction similar to volume of fluid. In that paper, we have also given physical interpretation to a direct delta function. This direct delta function in a diffuse interface method, it is mirrored across that red band, and we have physically interpreted it. We have shown certain derivations and given a physical interpretation of this direct delta function as an interfacial area concentration. Now, the improved level set method, diffused interface level set method that we had started working on a couple of years ago, although the idea was there for last 5 years, we have used this physical interpretation where we demonstrate in the formulation that in the diffused interface method you can apply the surface tension as a surface force, and the results which you will get will have very less mass error, and it will be even much more accurate than sharp interface method. So these are so just to give you an idea, let us suppose, so this is a black interface which you are seeing. So this interface is cutting on bottom surface and top surface. So the value of Heaviside functions, if you calculate, you can see that it is cutting more than 50% of the upper surface and less than 50% of the, as far as the fluid 1 is concerned. So the Heaviside function here on the north surface center is greater than 0.5, and on the bottom surface it is less than 0.5. This interface is not, so this interface is not cutting the left surface and right surface. However, the left surface is it is on the left surface, you can see it is completely filled by fluid 1. So the Heaviside function value is 1 here, and there is no fluid 1 on this surface, its value is 0 here. Okay, so the value of Heaviside function we have physically interpreted will give you an idea how much fraction of the area is wetted by the fluid 1. On the right surface, there is no fluid 1, there is no wetting, so it's 0. On the left, it is 100% wetting, so it's 1. Using this physical interpretations, this has been the, I would say, backbone for our, in the formulation for our improved diffused interface level. So this slide shows you a graphical representation of the computational stencils involved in diffused interface method and sharp interface level. Okay, there are some repetitions. Diffused interface is a single fluid. Sharp interface, multi-fluid approach. Surface tension is modeled as a volumetric force in diffused interface method, whereas it is modeled as interfacial boundary conditions. This is less accurate. Sharp interface method. So we started 20 years back with this method. Maybe around 10 to 12 years ago, we worked on that method, and today I am presenting a method. So in this method, we are in this paper which we wrote, we showed that this method gives better result than this method. Today I am showing a method which I will show that method is giving more better result than both these methods. Before I will emphasize, this model surface tension as a volumetric force. This model surface tension as a surface force. Today I am presenting method in this formulation, diffused interface. But I am coming up with a formulation where I am applying surface tension as a surface force. And then I will show you a series of test cases 2D as well as 3D and demonstrate the effectiveness of the improved diffused interface level sets. Now, whenever you want to develop a computer program, you need certain ease in implementation. So one of the advantage of this diffuse interface method is it's much simpler to implement because it follows a single fluid approach. And moreover, nowadays we work on problems which involves multiphysics. So when you want to unify compressible and incompressible flow in is much simpler in diffused interface approach. It can be easily extendable to complex geometry problems, non-Cartesian, non-cylindrical problems. And there is no requirement to track interface implicitly, as surface tension is defined at the face and surface. This I'll discuss a little more in detail. Okay, now when I say drawbacks of the presently diffuse interface method, this is with reference to the improved method which I'll be presenting. The existing diffuse interface method models surface tension as a volumetric force and pressure as a surface force. So one, like in CFD, we have pressure velocity decoupling. In classical CFD, on the classical CFD books you might have gone through. We believe that modeling of surface tension is leading to improper pressure interfacial force coupling, and this is what we have tried to overcome in this method. The present diffuse interface method has been shown it leads to high spurious current, especially near to the interface for high density ratios problem. So, and when you go to computational methodology for diffuse interface method presently, in computational methodology we use a predictor corrector approach. The surface tension is implemented in the predictor step while pressure comes much later in the correction steps. So these two, pressure and surface tension, they are used in different steps of computational algorithm, causing further decoupling between them. So the research question which we asked is, for diffuse interface level set method, how to implement surface tension force as a surface force and improve the coupling between the pressure and surface tension. So when you look into the surface tension as a volumetric force, it's expressed as shown here, product of sigma, which is force per unit length, curvature, whose unit is 1 by length square. So sigma into k makes it force per unit 1. This is a direct delta function, and this is normal to the interface. So this is force per unit 1. For level set method, this direct delta function is expressed as gradient of Heaviside function with respect to the level set function. So if you substitute delta as dh by d phi, and this normal unit vector level set method, it is given by d phi by grad phi divided by mod of grad phi. Finally, when you substitute normal distance function in terms of level set function and delta, you can express the volumetric surface force as sigma k grad of h. Now, when you look into the Navier-Stokes equation, the pressure term is grad of P, and when you have grad of P and grad of H, the idea which we have used is, here our objective is to improve pressure and surface tension coupling. So in the next slide I will show you that we will convert, because any CFD methodology conventionally it starts with a volume integral. So I will show you in the next slide. We'll take a volume integral and then use Gauss divergence theorem, convert into surface integral, and the way we will be dealing with Heaviside function will be similar to the way we discretize the pressure force. So, like any finite volume method, we do volume integral and then the volume integral is converted into surface integral by Gauss divergence theorem. And when you convert this into surface integral and then use a finite volume discretization. Now let me explain you few things. Now let us take this first term He. So when you do this surface integral, it will get converted into, you have Cartesian coordinate system. So this will be east minus west Heaviside function into delta y and north minus south. Now here I would like to point out the value of the Heaviside function on the east surface minus west surface into delta y. This is representing what? This is representing the x component. This is the black line is the interface. Normally our control volumes are very small. So locally I can assume it as a linear. And this surface area, if I assume it as a linear, it has two components. One is this is the x component and this is the y component. And it can be shown through a physical interpretation that this difference, this term is equal to the x component of the interface, surface area of the interface, and this is the y component of surface area. And then the surface area force, when you substitute this Heaviside function in terms of the x and y component of the surface area, you end up with a formulation where this volumetric force by this formulation is reformulated into a surface force. Now when you do this, then while we go to the solution algorithm, so when you develop a computational methodology, we do not use this in the predictor step. It comes in the pressure Poisson equation later on. And so, as I said, that when you go to the computational methodology, you use a predictor character step. In the predictor step, in the traditional diffuse interface method, in the predictor step, the surface tension force used to be, but it is not here in this case. And so there is a predictor step, there is a corrector step, and when you take the difference of the two, you end up with pressure correction equation or a pressure Poisson equation. So in the corrector step, finally, when you develop the pressure Poisson equation, you can see that in the pressure equation, this B term, which includes the surface tension term. So the pressure and surface tension are coming in an equation, in a single equation. So this way, we are saying that this formulation is having a better pressure interfacial force coupling. And then we have done a series of performance study. So we developed both in-house 2D code as well as 3D code. And there are standard test cases for which we have done some comparisons. We have done a systematic comparisons. So the simplest of problem in multiphase flow development we start is a static droplet case, and then we have went into. So in this case, static droplet case, we don't need to solve for flow. The relaxation, but you have to solve full Navier-Stokes equation in the rising falling droplet and rising bubble test. So this is a static droplet case where there is a droplet, and by Laplace law we know the solution for it. What will be the pressure drop, and which is given here, sigma by r, and we have taken the input parameters as shown here. The radius of the drop is taken as 2 mm, and we have done this study for various density ratio as high as 10 to the power 5. And in this test, people normally calculate two things. One is the maximum spurious velocity. The velocity in this problem in the domain should be ideally 0, but numerically when you solve, there is some velocity which is generated, spurious velocity near to the interface. So in such test cases, the value which is observed is what is the maximum numerically generated velocities in the domain. And second, from Laplace law, although we know what should be the pressure drop, but numerically we also compute how much pressure drop we are getting. And these test cases are normally done with two, I would say, cases. This problem is done on two cases. One, if we specify the curvature, because once you know the radius, it's a static droplet, you know the curvature also. So if you specify the curvature and do the simulation, or if you compute the curvature. So there are two cases for which we have done. And so the parameters of interest are this maximum velocity, which should ideally it should be 0, but these are numerically generated velocities, and the error in the delta p, that is. So here I am showing you three different results. Direct delta or the traditional diffuse interface level set method, improved diffuse interface level set method. We have considered three different density ratios, and the improved diffuse interface versus traditional. When you compare the magnitude of the maximum velocity, there is about 8 order of magnitude reduction in the maximum velocity. If you again compare with the delta p values, the error, this is error. The error, you will see there again there is a remarkable drop in the error in the improved level set method. And in our earlier work, we have got this result for sharp interface. So if you compare the results of improved diffuse interface with sharp interface, they are much closer as compared to the earlier two cases. So with this we are showing that the spurious velocity computation as well as the error in pressure drop across the interface for a static droplet, the improved diffused interface level method is giving results close to the accuracy of sharp interface level set method, but much better than the traditional diffuse method. This we had done for computed curvature, but when you do for computed curvature, when you compute the curvature through your code, then there is some additional error which comes in. So in this case, the pressure drop across the interface is 10 to power minus 11, but here is 10 to power minus 3 because computing curvature leads to some more errors. However, in the computed curvature case also, the maximum velocity between traditional diffuse interface and the improved, there is a remarkable, here you have a remarkable improvement, but here there is a improvement, but not that big. But this is close to that for the sharp interface levels. We have plotted graphs for comparing these errors also. So here this is for velocities, the spurious velocities inside the domain, and this is the surface plot for the pressure variation. Ideally, there should be a sharp change in the pressure across the interface as shown here to the surface plot. But the traditional diffuse interface method, there is some oscillation of pressure across the interface. This is the results with exact curvature. This top row is for traditional diffuse interface level set method. This is with improved diffused interface. In the second row, you can see the results are the spurious velocities are much smaller. The pressure change across the interface is much sharper. The first row is traditional method. The second row is the improved method. Also note that this simulation has been, this result which I am showing you is the density ratio of 10 to power 5, which is the most severe case. So this problem, we have the freedom to choose as compared to experiment whatever we want to set in. So let us suppose you take a square drop. So it will, as you proceed with the simulation, this square will finally, all of you know, it will reach to the circular shape. So this test uses pressure surface tension coupling under the effect of advection and diffusion, which we have not used in the previous test. So you can see that we have considered square droplet and rectangular droplet, and this is with the improved diffused interface level set method, and finally it approaches to the circular cross section as expected. And the first row here is a diffused interface and bottom is an improved, and here also the spurious velocity is with the improved one. Here it may not be that much visible, but when I show you the table or quantitative values, you can see it. So this is the maximum velocity. The red color corresponds to the improved method, and the green is the traditional method. So the improved method is leading to much reduction, much smaller spurious velocity. For level set method, this is the biggest of the plot, mass error. And we are very happy to see that the improved level set method, the mass error is very low. That is one. Second thing, with respect to time, it is almost constant. Whereas the traditional level set method, there is an increase in mass error with time. We did two more test cases, falling droplet and rising bubble. So this is a water droplet falling in air. The second case is a air bubble rising in water. And these are the input parameters, and basically we plotted the centroid position of the droplet during fall or rise. This video is very slow and there is not much change, so you may not be finding much change, but that's a rising and this is a falling droplet. And this is the results which we compared. This we had compared with some previous published results, and here also the diffuse interface, the improved. The blue one is the improved diffused interface method, which is having a better matching. But the more interesting thing is, as you change the grid size, with level set method, earlier mass error is one of the biggest problem, but when you keep refining the grid, the mass error reduces. So this bar chart, the pink bar which you are seeing are the traditional level set method, diffused interface level set method. On the traditional level set method, 40 by 60, when you go to 80 by 120, there is a drop in error. But when you see this yellow curve, yellow bar corresponds to the modified method, the improved method. In the improved method, there is a reduction, but already it's very small, and then so it's almost constant. There is not much effect of. There is a slight decrease, but as compared to the traditional method, the improved level set method is performing much better, and this is the biggest of disadvantage of level set method as compared to volumetric. Similarly, we compared the maximum error for the rising bubble. We plotted with respect to time what is the maximum error in the centroid position and the aspect ratio of the droplet. And the improved method gives a smaller error as compared to the traditional. Finally, we developed in-house 3D solver also using this methodology, and we did similar test cases, 3D static droplet, relaxation of non-equilibrium, non-circular droplet, and 3D dam bed and droplet collision, non-axisymmetric bubble merging, and non-axisymmetric bubble collision. Here again you can see that with exact curvature, there is a sharp reduction in maximum velocity, and there is a sharp reduction in the error with the improved level set method as compared to the traditional method. Here again, with respect to time, we have plotted the delta P, and the red is the improved one, which is much smaller as compared to the traditional method. This is the maximum velocity, and similarly for the complicated. This is the 3D simulations we have done for the cubic droplet, and here again you can see the with respect to time, the improved method has much smaller Umax, and you can see mass error. Mass error is maybe slightly more than 1%, and it is not varying much. Whereas it is here, with respect to time, it is increasing from 4% to maybe 8%. So you can see clearly that this orange bar. Now here, this is the plot of mass error with respect to bit size. 20 cube, 30 cube, 40 cube, and the error For traditional method is reducing from 35% to 28 to 5%. Whereas the improved level set method, it is close to 3% and then it is dropping to 1%. So I would believe that this mass error is the biggest of improvement in the development of computational methodology with level set. This is for non-equilibrium cubic droplet, and here again similar conclusion can be drawn. This is a 3D band break test case which we have done, and here again the red one is an improved level set method which is compared with the experimental result of Morton and Moyes, and here again the improved method is having much better comparisons with the experimental. Then we did 2 droplet coalescence in a 3D situations. Actually, this is an axisymmetry problem. This we did for comparison, validation. But later on, we did pure 3D problem, which is a non-axisymmetric bubble merging. And in this case also, if you compare the mass errors, this is a 3D simulation, so we had not gone into very fine details. But still, you can see that the variation of mass error with respect to time, the improved interface level set method. Although in this case 3D problem we are seeing that the mass error is increasing with respect to time with improved method, but still the mass error is much smaller as compared to. If you compare here the error of the mass error, you can see that the traditional method there is a sharp reduction from 50% to 12%, whereas with the improved method the reduction is from close to 15% to 8%. And we did 3D non-axisymmetric bubble collision simulation also, and we compared with experimental results as shown here. This is the variation of mass error, which is, as I said, that our grade was little not very fine grained, so still the error is close to 10%. But we believe, but still at least you can conclude that on this grid size, the improved method has much smaller mass error. It is close to 10% as compared to, this is rising and this is almost constant. So with this I have come to the end of this talk, where we have proposed, so in our previous work we found that sharp interface level set method gives more accurate solution with a substantial reduction in computational time as compared to diffuse interface. And in this work, we have come up with an improved diffuse interface method which is to give accurate solution as well as with substantial reduction in computational time as compared to the traditional diffuse interface. This work was done by my last MTech student, and presently we are using this code for 3D simulations for a wide variety of problems. Thank you for your attention and welcome.
Yeah, one question. Thank you for this nice talk. If I understood you correctly, you moved the surface tension implementation from the predictor step to the corrector step.
Corrections. Pressure.
Yeah. Is this all what was necessary to achieve the better results?
That was not the all thing. Another thing is the formulation that we did. Because we converted using the physical interpretation of Heaviside function, we converted volumetric force to a surface force, and then we brought it to the pressure poison.
Okay, and could you use this formulation in the predictor step also, or
no? It's not at all there.
Okay, thanks.
So in terms of extension to problem involving phase change, for example, which of these formulations is easier? The sharp interface level set?
Diffuse is much easier. Much easier. Especially when you go to phase change, you have a interfacial mass transfer. And
sir, how do you in this thing? How do you calculate the curvature?
yeah,
like you mentioned there is some error in anything, so the curvature calculation is done.
So there is an expression for curvature in terms of level set function. It's a differential term. Discretization. can calculate the curvature. So any discretization use, there is some order of accuracy. There is some numerical error which is there.
I mean, how does it compare to the other ways of calculating curvature?
Yeah,
Say
so
the
there
height
is a
function.
scope. There are different ways of calculating curvature. So we have not looked into better, more accurate way of calculating curvature. If we do that, we can improve the results further. Yeah.
So I have another question. So you have compared this with the terms of the mass error on these three methods. But there's another thing always in commercial Multiphase is Fourier's current. Right? When we have a very sharp curvature or the this triple point being formed where the curvature is contacting the surface, there is always Fourier's current. So in terms of Fourier's current, how these three methods differs, good, bad, or difference?
Yeah, you are talking a more complicated problem, but for a simpler problem, static droplet, we had compared. I had shown you the tables as well as the figure. I had Umax in my so that was the spurious velocity. For static droplet, I had shown. But we need to do for a more realistic problem.
Is this method of using the Heaviside function basically from a diffuse interface perspective, can it be also done not only in your solver but can be done in any open source code like OpenFOAM?
Yes. Yeah.
So that we can extend it to general unstructured
Yeah,
solver
yeah.
which can
In
handle
fact,
complex 3D.
yeah. In fact, one of our PhD student is extending this for complex geometry problems. It is easy to extend to complex geometry problems.
Right.
Yeah. Sharp is too complicated.
Yeah.
Diffuse is much easier. But if we, so this method demonstrates you can get as accurate a solution as Sharp with easier implementation. So that way you can go for compressible flow and complex geometry. So the CFD development can be much easier.
If there are no other questions, let us thank the speaker.
Thank you, Professor Atul Sharma. And I request Professor Sanjeev Chandra sir to present.